All right, welcome back, or at least to another physics lecture. This one is going to be about Newton's first law of motion. And as you can see, I indicated this is now officially sort of the beginning of part one of this course. The last lecture, the first lecture, was sort of just some background, not necessarily physics, but things that might be useful for you to know. Right? Math and science, so generally speaking, about math and science. Right, so now we're going to get into some actual physics, and to begin with, we start out with mechanics. Right? So mechanics is another way of saying how do things move, right? How do things go from one place to another? How do they do it when at a constant rate? How do they do it when that rate changes? How do they turn around? Right? All about how objects move. Also sometimes referred to as kinematics. And, well, there's no really ways about it. Newton is a very well-known physicist, and for a good reason, in that he basically just came up with, or codified at least, the way that things sort of move in what we call Newton's three laws. Three laws of motion. So yeah, so this first lecture is going to be about the first law. So before we get to the first law, we're going to go through a little bit of background and sort of lead up to Newton. And to begin with, well, we can look back at least to the ancient Greek times and to Aristotle, who you could say was a scientist. He was doing exploration. I think a lot of people would say he founded a number of different areas in science, like biology for one. He was more of a philosopher and not necessarily a good scientist. You say that mostly because he didn't really seem to take the idea of testing his theories all that much to heart, right? And being willing to admit when they were wrong. Some of his theories, it seems like, if you just tested it, it would seem like it would be pretty easy to prove wrong. So it took a few thousand years until Galileo came along and was much more accurate and was doing science, was making theories as hypotheses, was testing those hypotheses, and coming up with formulas and using mathematics to describe his theories and results and make predictions and all that sort of thing. So this is one example where there's that attitude of science, so there's that way science is supposed to be, and then there's also, humans are the way we are, and you can have somebody who is just so well thought of, like Aristotle, that his ideas were just sort of taken to be true for a very long time. So this was not a very scientific way of going about it because, like I said, if you would have really dug into and questioned his theories, it wouldn't have been all that difficult to prove something wrong. Okay. So this is at least for some of what Aristotle was talking about. In particular, thinking about Aristotle's sort of theory of motion, how things move around. So his idea was basically that there are two sort of states of every object, and depending on what the object is made up of, it has this natural tendency to want to do something. So you have, it's kind of a lot to describe, but you have things that are made up of, say, like Earth-like things. Right? So this is before we had the ideas about atoms and elements and things like that. So it was the fundamental things were sort of earth and water and wind. Right? So if you have something that's Earth-like, so like a stone or like, I guess, a person or an apple, right? Their natural tendency is to be drawn to the earth. Right? So that's why if you release a stone, it falls to the earth. Right? This is Aristotle's theory. And he was also, part of that theory was that a heavier object, Earth-like object, is more strongly attracted to the Earth. It has a greater tendency to want to get pulled to the Earth, so it will get pulled faster towards the Earth. So if we were to compare or look at a picture of what Aristotle's theory would say about dropping, say, a ball of wood versus a ball of iron, for Aristotle, the iron is heavier, but it's the same size. Iron is much more dense. Iron is going to be heavier. If I were to drop them, the iron being heavier means it's going to get pulled more strongly to the Earth. Right? So if you look at these as being like sort of snapshots, drop, 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 the wood's going at a certain rate, the iron's going faster. Well, hopefully you know, but if you didn't know, that is incorrect. Right? The speed or the rate at which this object speeds up as it falls towards the Earth does not depend on the weight or the mass of that object. So in reality, if you were to take those two spheres, or those two balls, and you were to drop them, they fall at the same rate. This is one area where you would have thought that you take a stone, and maybe a much smaller stone, and you just let it go, they hit the ground at the same time. Maybe Aristotle's wrong. Yeah, so Aristotle had this idea of motion as sort of being like an unnatural thing. Like, so for an object to be in motion, it's unnatural, so there has to be something that causes that object to stay in motion. So, you know, if we were to look at this picture of like a cannon firing, there weren't cannons back then, but we can place his ideas onto this picture and say, well, his idea would essentially be that there's this sort of unnatural state where the cannonball has been pushed out of the cannon, it goes a certain distance, and then it enters its natural state, which is just to fall straight down. Again, this is not how reality works. In reality, the cannonball will shoot out and also drop at the same time, right? That arc was probably a lot further along, unless it's a very weak cannon, but you get the idea, I think. Yeah. So he had ideas of why things kept going in motion when they weren't being pushed, and it had to do with like the air moving around and moving back in and kind of pushing along still. It was a theory, it was scientific, and the reason it was scientific is it could be proven wrong, and it was proven wrong. Aristotle's ideas of motion are incorrect. So one of the most famous examples of a scientific experiment, which may or may not have happened, I've heard that it might just be sort of a story rather than an actual thing, was that regardless if it did happen or not, it's a good story. So, well, we'll talk about what Galileo actually did. We know for sure he did. Might not have actually gone on the top of the Leaning Tower and dropped some stuff. But if Galileo had taken these two balls, say like a bowling ball and a basketball, or whatever, two balls, one's much heavier than the other, you take them all the way to the top of the tower, Leaning Tower of Pisa, and release those balls, to the crowd's astonishment, after you release those balls, the heavier and the lighter one fell at the same rate and hit the ground at the same time. So in that simple instance, you proved that Aristotle's theory of motion is incorrect. You might be wondering, well, why does a feather not seem to fall so quickly, or a piece of paper not seem to fall so quickly? It turns out that has more to do with the fact that it's falling through something. Even though you don't see the air around you, there's air around us, right? So that air will cause resistance, air resistance, which ends up pushing back against an object that's moving through it. So when you have something that's like a feather, it will have a lot of air resistance, versus something like the sphere, which doesn't have quite as much. So we'll talk more about air resistance in things falling and how that affects it But in general, if there was no air resistance, then things would fall at the exact same rate. And you know, for the most part, a bowling ball and a basketball, very similar air resistance you get, so they would fall at the same rate, even though they're very different in weight. Okay, so that's the sort of story that gets told about Galileo. The thing that Galileo for sure actually did was look at objects rolling down inclined planes, right? So planes that are at an angle, put a ball on it and roll it down, and kind of observe how it moves down, how far it moves in each second, say, how fast it's moving, things like that. Okay? So if you were to think about the motion of a ball, or like a sphere that's rolling down a hill, if you imagine, well, you put that sphere on a downslope, then the ball is going to roll down it, and it's going to increase its speed as it rolls down. You can watch it; it will get faster and faster and faster, right? And if you increase the incline of that speed, if you make it steeper, it's going to happen even faster, right? It's going to speed up, but it's going to go faster and faster, and it's going to happen quicker. And the other side of that is if you decrease that angle, it's still going to roll and it's still going to increase its speed. It's just going to be, that increase is going to be a bit slower. On the other end, if you try to roll a ball up a hill, right? You try to roll it up, it slows down. Eventually, it'll come to a stop. Right? If you try to roll it up a much steeper incline, it'll slow down even quicker. It won't even go as far. If you try to roll it down a less of an incline, right? It'll slow down, but it'll slow down less or slower than it did at the middle. So it'll go a bit further, but it'll still slow down eventually and stop. So this Galileo's idea was that, well, if it's on a downslope, it speeds up. If it's on an upslope, it slows down. So ideally, what's right in the middle of speeding up and slowing down? What's in this horizontal flat surface, right? Well, between speeding up and slowing down is not changing your speed at all. So he could hypothesize that if I have an ideal situation, I have a ball rolling along nicely on a flat surface, it shouldn't speed up or slow down, it should continue rolling forever. So this is the beginning of a thinking where the natural state of this object is actually just to continue what it's already doing. Alright, so this is just kind of an extension of that last slide, right? So not just imagining a ball just out of nowhere rolling down a hill or a ball rolling up a hill. If we can imagine then, and Galileo could do this as an experiment, was essentially make a kind of track for balls to roll along, where you have it start up on one side, it's on this downslope. So we'll roll down and we'll roll across, and then it's going to roll up the opposite side, right? So then it goes to uphill on the opposite side. And if you do this, where you have the downslope and the upslope basically the same here, then the ball's going to roll down, it's going to roll across, it's going to roll up, and it's going to stop. And it stops essentially at the exact same height that you started out at, right? So you let it go at this height, it goes down, it goes up, down, across, up, back to the same height, and then it's going to probably roll back down. Well, so if you then take the opposite slope, that uphill slope, and you decrease the incline a little bit, right? So you make it a shallower uphill climb. Then still, as is shown in the picture here, you release that ball, it's going to go down, it's going to go across, it's going to roll up, and it still wants to roll up to the exact same height that you let it go at. But now that that uphill is been angled down, it needs to go further before it can reach that same height again. Right? So the second picture versus the first one here, the balls roll across and they roll up to this final height, the same height that they started at, in that final position, but since we have this less of an incline here, it has to roll further out. And again, Galileo could imagine this and theorize or hypothesize that, well, the ideal sort of situation is that if I imagine I keep decreasing that uphill slope, right? So keep bringing down this incline side, and eventually, well, it's got to go, every time you decrease that slope, it's got to go further and further away in order to reach that initial height again, right? Because it wants to come down, then come back up to the same height that it started, right? So if you're taking that slope down further and further and further, it's got to go further and further out until it reaches that same height. And the extreme of that is that if I have a flat surface, no incline, it's never going to reach that initial height that it started at, because it never comes back up. So again, it should continue on forever. So all of these experiments and sort of hypotheses and so to the ideal situation are questioning still Aristotle's idea that this natural state of things is to just fall and stop. So I should probably say something about friction at this point, because you might be thinking to yourself, well, if I roll a ball down a hill, it doesn't keep going forever. I don't care how flat the surface is at the end of the hill. And you would be correct. That is because there is actually something that is acting on the ball. There's something that's trying to change the motion of the ball. Instead of it continuing to roll on forever, there's actually a force that's acting on it, and that force is a frictional force. And also a little bit of the air resistance too, as the ball runs into the air in front of it. So we're going to talk more about friction and air resistance, if not in the next lecture, then the lecture after that, so not too much about it now, but just to say that friction is something that always acts against the motion of an object. Okay? So for instance, when you slide along on a floor, friction is pushing back on you against the direction you're going to try to slow you down and eventually stop you. Or if you jump out of an airplane, another kind of friction, air resistance, will stop you from speeding up indefinitely. You'll jump out, you'll speed up to a certain velocity, which is what's known as your terminal velocity, and then you won't keep speeding up anymore. Right? But again, it's the friction is the force that's acting against you in order to stop you from continuing the changing, or to just kind of, to act against the motion that you're trying to do. Right? So in the case of the ball rolling down the hill, the ball does roll down the hill, and if there were no friction or air resistance, the ball would continue to roll on forever. And we can actually do those kinds of experiments in free fall situations or in very microgravity situations with very low gravity, or even surfaces that are just very, very smooth. But yeah, so that's sort of why I maybe kept qualifying his ideas when Galileo was talking about these experiments. You could imagine the ideal situation where there isn't any friction, there isn't any air resistance. In that situation, the ball would just continue to roll forever. So in talking about friction, I explained or said friction is a force, and I've used the word force, I think, before. And since we're almost at the point where we're going to state Newton's first law, we need to understand what a force is, what I mean, at least at some level by a force, because Newton's first law involves that word. So, at a very basic sort of level, a force is just something that pushes or pulls on an object or a thing. So, if I push against a chair, push against a chair, then I'm just acting a force on that chair, right? The force is that push. Right? Or if I, tug on the chair or something, or I tug on a rope, then I'm acting a force on that rope, I'm pulling on that rope. So remember this idea of a vector, that a vector is something that has a length or a magnitude and a direction to it. Right? So force is what we would call a vector quantity, meaning that to describe a force, I need to say how much force I'm pushing, or the amount of force I'm pushing with, and in what direction I'm pushing. Right? So when I say I push on a chair, right, I can say, well, I can describe, maybe I'm pushing with, say, 50 newtons of force, and I'm pushing, away from me. Direction's a little bit arbitrary, depending on your perspective. I think maybe this is to the left for you. But the amount and the direction is what comes into describing a force. And we'll talk a good bit more about forces for Newton's second law, but we do need this concept for Newton's first law as well. So another basic, or not necessarily basic, but fundamental concept for Newton's first law is this idea of inertia. Right? So inertia it's not a vector, it's just basically a property of matter. And when I say matter, I mean things that have mass. They're made up of atoms and things like that. So it's a property of matter to resist changes in motion. So if something's moving, it doesn't want to stop moving. If something's not moving, it doesn't want to start moving. So the amount of inertia you would say that an object has, well, it depends on the amount of matter, how many atoms make it up. Yeah, it's technically, you could say the inertia is proportional to the mass of the object, or the amount of matter that makes it up. Okay, so force and inertia. And then, here we go, for Newton's first law of motion, is stated as an object at rest will remain at rest, and an object that is in motion will remain in motion, in uniform motion, meaning motion in a straight line with a constant speed, unless a force acts on that object. So this is at least one way of stating Newton's first law. It's one of the more common ones. You say an object's at rest. If an object at rest, it will remain at rest. If it's in motion, in uniform motion, it will remain in uniform motion, unless acted on by an outside force. So what that means is that, like it's easiest to think about these things in the ideal situation. So maybe imagine watching an astronaut in the International Space Station, and they sort of take an object, whatever it is, maybe an orange or something, and push it, it'll start to move along, right? So it's moving along at this constant speed in a straight line, so this is uniform motion, and it's going to keep doing that unless another force comes along to change that motion. Another force maybe being, hits the wall exerts a force back on it to stop it from going that direction. Or maybe somebody grabs it and exerts a force backwards to slow it down and then stop it and hold it, right? The other example, or the other side of that is that if it's, you just let, say, that orange go, then it's going to float in space. It's going to float in the same location, meaning it's just at rest. It's not moving, relative to you at least. And it's going to remain that way unless something comes along and acts a force on it to change that. Right? So that would be then somebody coming along and pushing on that orange and then starting to move. So one way to think about Newton's first law is essentially it's just a statement about inertia, about objects that are massive, have inertia. And essentially that all boils down to any object with mass will resist a change in its motion, in the way that it's moving. If it's not moving at all, it doesn't want to change that. If it's moving already, it's moving in a straight line, it doesn't want to change that either. Okay, so Newton's first law, you know, it could be thought about in this sort of implication way, like an if-then sort of statement, and these statements go in both directions. Right? So if you start out with an object and it's at rest, and it's not moving, that means, that will tell you, or it implies, there's no force acting on that object. And before I move on to talk about forces still here, I should note that Newton's first law technically is about not just any single force, it's essentially all of the forces together that act on an object. If you look at the sum of all of them, how they all, sometimes they push against each other, sometimes they push with each other, sometimes they pull against each other, right? You look at the sum of all those, we call that the net force. And if there's no net force on that object, so if all the forces cancel each other out in some way, right, you push this much to the left, you push this much to the right, you push the same amount, then there's no net force. There's going to be no net push or pull on that object, right? So technically Newton's first law is about net force, if there's no net force on an object. So again, if an object is at rest, you can infer that there's no net force acting on that object, or net forces, or all the forces sum up to zero, so now they cancel each other out. Also, if an object is in uniform motion, meaning it's traveling in a straight line at a constant speed, you can infer then that it also, in that case, there's no net forces acting on that object. And again, these statements go go both ways. If you somehow know there's no net force on an object, you can infer that object is either at rest or in uniform motion. Okay, so think about a little example and watch a video that's kind of related to it, or similar to it. But an example of Newton's first law and inertia in general is if you take some carts, and these carts are going to be on wheels, and if you stack, say, a few of them on top of each other, and kind of push them all together, so get them all going. Okay? So they're all moving at this constant rate, assuming that very little friction or whatnot, or air resistance, and they're just going to continue going at a nice constant uniform motion, right? So they're all moving together in this uniform motion, and they want to continue to do that. So they're going to continue to do that unless something acts on them, some outside force acts on them, some net force acts on them to stop them. Right? So in this picture, the carts are different sizes, so when they encounter the wall, the first one encounters the wall, this large one encounters the wall first, so bam, there's a force on that bottom cart, and it acts against the motion in order to stop it. Right? However, there's no force that's been acted on the top two carts still, so Newton's first law and the property of inertia says that they're going to continue moving in that uniform motion until a force acts on them. Right? So the next thing that would happen would be that second cart would hit the wall would impart active force on it to stop it. Right? Then the third one would keep going until finally it hit the wall and it would stop too, or they might bounce back. Okay, so let's see maybe a video of that happening. So it's slightly different because it's actually a stack of books on a chair, and we'll right? But all these things are in uniform motion. The chair, this rolling chair, hits the other chair. So the rolling chair has had a force that acted on it, so it would actually change its motion, right? It was in this nice uniform motion coming towards the other one. And the second chair was there, so it ran into it, it acted a force on it, it changed its motion, right? But what you saw was that the books, they didn't hit anything right away, and the stuffed doll here didn't hit anything either. So they wanted to continue going in that same direction. And they did continue until they hit the wall after the chair. There you go, inertia. Yeah, maybe another interesting demonstration of Newton's first law in inertia is if you take a stack of washers, it's metal discs, you can do something interesting, or you can see inertia sort of in action, if you are able to basically hit one of those discs individually. So the washers are all massive, they're all made up of matter, right? So they all have inertia, and they all don't want to change from their current state, which if you just stack them here, the current state we would say they're just at rest. They're sitting there at rest, right? So, yeah, let's see what happens. Okay. So we have that stack of washers, and what he's going to do is he has a ruler, I think of some kind, or something flat, hard object here, and so that he can actually act a force on one of those washers at a time, say like the bottom washer, right? So if he uses that ruler to smack the bottom washer, then you're acting a force on it. So Newton's first law says, well, you're going to change its motion, you're actually going to cause it to move to the side, right, in the direction that force was acting. But the rest of the washers, you didn't act a force on those, so they're not going to want to move, right? No force, it's going to want to remain at rest. There you go, you can just slice the washers out from underneath, and the ones on top just want to stay where they are. I guess he's probably practiced this. It seems pretty good at it. So there you go. The inertia of these objects means that they don't want to change from their at-rest position, so only the ones that are getting hit, you're actually acting a force on, are you're going to cause to move. The rest of them stay at rest. To say that there is a little bit of, you might be thinking there is a little bit of a force because when you hit one of the washers, the contact of that washer to the washer above it, there's a little bit of friction in between there, so there's a little bit of force, but not enough to actually get any of those other washers moving. Okay, so one other example of inertia would be if you've ever yanked on a toilet paper roll, you might have noticed that all other things being equal, if the toilet paper roll is almost empty and you try to yank down on the end, then you are just going to quickly unwind the toilet paper roll, right? You're going to pull the rest of it out. And that is as opposed to if that toilet paper roll still is basically full and you yank down on that, then you're probably just going to rip off whatever part you were yanking down on. Right? So this is another example of inertia, because when the toilet paper roll is almost empty, then it has less mass, right? So remember, the inertia of an object, it's that property that resists changing its motion, or its state of motion, depends on how massive it is, how much matter makes it up. So with that nearly empty roll, there's not a whole lot of mass there, it has less inertia. Versus the larger roll, more mass there, more inertia. So the smaller one, the almost empty one, essentially has less of an ability to resist a change in its motion. So when you go to yank on it, it doesn't have that much inertia, so it just starts to roll around. You change its motion from being at rest to twirling around there. Versus the bigger roll, it has more inertia, so you pull it at rest, or you try to yank on it, it has enough inertia to resist that change in motion, so the whole roll stays at rest and you just yank off the piece. Alright, and you can imagine another example of inertia, and, well, related to some historical stuff, I guess, where the idea of inertia, or the tendency of an object to remain at rest or in uniform motion, was probably around for a while, but was kind of dismissed for a long time. And one of the reasons was that, say, when Copernicus proposed the Earth was actually moving around the Sun, and not the Sun moving around the Earth, people thought it was just ridiculous that the Earth is moving at all. Because if it was, how would something like a bird drop off of a tree branch, be able to swoop down and grab a worm? Right? So the thought was that, well, if the Earth is moving and the bird leaves the tree branch, then the Earth is going to be moving, and the bird's going to it's going to get sort of passed by the Earth, and it will miss that worm entirely. Right? So the bird jumps off, the Earth keeps going, and the bird's out of luck. Right? However, the idea of inertia means that even though the Earth is moving, the bird's also moving too. So it's already in a state of motion along with the Earth. So to say when the bird jumps off the branch and goes down, the bird's already moving in this motion along with the Earth. So even though the Earth keeps rotating around and also moving around the Sun, the bird's also doing that. So by jumping off the branch, it doesn't lose that motion, it just adds on some extra motion of it going down to pick up the worm and coming back up. Okay, so a little question for you. The first of probably many in this course. And I'd like you to take these as questions where you, well, maybe you know the answer right away. If you don't, then hit pause before I switch to the next slide and show you the answer. And try to, well, think about it on your own. Select, if it's a multiple choice one, write down which answer you think it is. If it's not multiple choice, write out your answer, whatever you think it is. And then unpause the video and look at the explanation. Hopefully you're correct, but if you were not correct, then that's totally fine too. I just hope that you understand then why you weren't correct, and so maybe you'll be more understanding of the concept. Okay, so in this question, you're imagining you're riding along at a steady speed in maybe a train or a plane, doesn't quite matter what, but you have a coin and you toss that coin up in the air, right? Remember, you're moving along at this steady rate. Where is that coin going to land? A, B, C, or D, right? So take a minute, think about it. Okay, well, hopefully you said C, that the coin will just land in your hand. Right? And it will do that for the same reason that the bird can swoop down and get the worm without the worm and the earth whizzing away from the bird. Right? So when you flip up a coin in the air, the coin, before you flipped it, and even after you flipped it, it already is in this uniform motion along with you and the train or the plane, whatever vehicle is taking you along. Right? So it already has this uniform motion going forward, and when you flip it up in the air, you're adding this sort of upward motion, but you don't actually change that horizontal motion. So that's why when you flip that coin up, it goes up, and it just comes right back down, from your perspective at least. Okay, so back to talking about just forces, and particularly when there's more than one force acting on an object. So, you know, like when you're pushing on a table one way and somebody doesn't want you to push on it, so they push on it the other way, right? You're both acting forces on that table and you're opposing forces. So the net force on that object, or the total amount of force on that object, is going to essentially be the difference between the pushes or the forces that you're each exerting. So this idea of summing up forces, or looking at all the forces that are on an object and kind of summing them up, involves looking at how much force, or the magnitude of each force that's being exerted, and in what direction that force is being exerted. So looking at force, again, as a full vector quantity. So as an example, if you imagine that there's like a brick sitting on a table or a surface of some kind, and maybe you take your right hand and you push along that brick a little bit, you push with 3 newtons of force. Then I guess you're going the other direction. Push 3 newtons of force here, right? Someone else comes along and they push with a bit more force in the same direction, right? So maybe they push with 5 newtons of force, right? Same direction though. So this idea of a net force or a total force is to say that those two forces, since they're in the same direction, are going to essentially just add together to be the same as or equivalent to an 8 Newton force pushing in that same direction. So the Newton is a unit of force. It's the way we measure an amount of force, at least in the metric system. In the standard, or whatever, the units we use here in America, they are pounds. A pound is a measurement of force. And a Newton is actually just about 1/5 of a pound. So 5 newtons is about 1 pound of force that you're pushing. So that other example was if you have, say, 2 forces that are pushing in the same direction, they can add together. If you have 2 forces that are pushing in the opposite direction, they're going to cancel each other out, right? They're acting against each other, so the difference of those forces is essentially what is going to be the net force in the end. So if you have that same brick and I'm pushing still with 3 newtons to begin with on the left of that brick. Somebody else comes along and pushes with 3 newtons on the right of that brick. Well, 3 newtons to the left plus 3 newtons to the right, overall, 0 force acting on that object, 0 net force acting on that object. Right? So this is to say that in the sum of all those forces adds up to being just 0. If instead I pushed with 3 newtons to the left and somebody else comes along and pushes with 5 newtons to the right, well, that's not going to be 0 net force overall now, right? Because the difference is going to be, well, 3 newtons to the left, 5 newtons to the right, is actually 2 newtons to the right, and the object's actually going to end up getting moved to the right, probably. So sometimes you say if there's, there's a bunch of forces acting on an object, but they all cancel each other out. They all balance out to be a 0 net force on that object. You might say that they balance each other out, or there's no net force on that object. All right. So another sort of question, or check yourself time, see how well this is sinking in. If you have these sort of 3 pictures on the left, and they're showing that there's 2 forces acting on a block of something, whatever it might be, if those are the actual forces acting, what is the net effect of those forces? What's the total force that's acting on that object? So I'd like you to, again, hit pause and try to draw the force acting on, say, the net force, the total force acting on, say, this first object, and we're drawing it as a vector like these other ones are drawn. So an arrow, and also indicate the amount of that force. Right? So like in this top picture, there's 2 forces acting on it, both to the right, first to the left, both in the same direction, and they're both 5 newtons. Right? So that's how we indicate a force. So I want you to be able to draw one arrow that indicates the total force on that object, right? And in these 3 situations. Alright, so hopefully you took a stab at that and came up with something like these, and if not, again, that's fine. It's better that you try, and then you're more likely to realize why you might have been wrong and remember it better later. Okay. So if you have 2 forces acting in the same direction, those forces are just going to add together. Okay. So 2 5-newton forces acting in the same direction is equivalent to a net force of 10 newtons in that same direction. Or, in the second case, a 5-newton force to the left and a 5-newton force to the right, since they're in opposite directions, it's the difference of them that's the net force, meaning 0 newtons in this case, because they're the same amount of force. The magnitudes are the same. And finally, the situation where you have a 10-newton force to one side and a 5-newton force to the other side. Well, again, they're acting in opposite directions, so the sum, or the difference of them, is going to tell you what the net force is. Difference being 5 newtons, and of course the larger force wins out, so the net is 5 newtons that way. That way. Yeah. Alright, one more question for now. Say you have a cart and it's pulled to the right with a force of 15 newtons, and it's also being pulled to the left with a force of 21 newtons. What is the net force acting on this cart? So go ahead and pause and give yourself an answer there. Alright, hopefully you said 5 newtons to the left. So again, these are forces, they're acting in opposite directions, one's to the right, one's to the left, so the net force is the difference of them, and the direction of that is going to be in the direction of the larger force, essentially. The larger force wins out. Okay, so another sort of interesting example of net forces, and how if you have an object that's at rest or in uniform motion, constant speed, a straight line, then the net force on that object is 0. So, right, that's just Newton's first law. So keep that in mind, and now, if we think of this situation where we have, say, this stick, and it's suspended between these two scales. Right? So you're holding these two scales, and the scales are just showing how much force the stick is pulling down on each of those scales. If we also hang a mass, something like an iron weight or something, off of that stick, then in total, the stick, since it has a weight, or the amount that it's pulling down, is going to be 2 newtons, and the iron mass is 10 newtons, then in total, there's 12 newtons that are kind of pulling downward right there, the stick and the mass together. So what that means is if I have these two scales holding it up, the sum of what those scales is going to show needs to also be 12 newtons. Right? Because if there's 12 newtons getting pulled down, there needs to also be 12 newtons getting pulled back up in order for this whole situation to be at rest. Right? The net force here needs to be 0. So in the situation shown here, we have that iron mass at one place, one position. It's a little bit more to the right side. And so the scale on the right is going to show 7 newtons, and the scale on the left shows 5 newtons, right? But in total, that's still the 12 newtons altogether. That's the same amount of force pulling down is getting kind of pulled back up here. If I were to shift that iron mass over even more, then this scale on the right here is going to show more newtons, right? It's going to be pulled down even more on this right-hand side. So maybe it goes up to 10 newtons, right? So if the scale on the right shows 10 newtons, how many newtons need to be shown on the scale on the left? Well, hopefully, you say 2, right? Because again, in total, the net force on this in this kind of situation is 0. So if there's 12 newtons pulling down, I got to show whatever newtons I'm showing on the one scale has got to add up with the other scale to be 12. So if I then shifted this guy maybe all the way to the one side, then this scale basically reads 12, that scale is going to show 0. Or if I shifted the iron mass right to the center, well, it probably should be evenly balanced, so this scale would show 6, that scale would show 6. This is, yeah. So exercising this idea of net forces, I guess, in the situation. Okay, so one other force we'll talk about in this lecture is what's sometimes called the support force. Also called the normal force. So the support force is just a broad term for the force that any surface exerts on an object when you place an object on that surface. Right? So in this case, the picture shown here, we have like this gold brick, and it's placed on a tabletop, right? So the tabletop is actually exerting a force on that brick in order to stop it from essentially pushing through the table or crushing the table. So that's why it's sometimes called a support force, because you're sort of, it's the force that supports an object on a surface, right? So if the brick weighs 100 newtons, meaning there's 100 newtons of force that's pulling it down, then the support force from that table also needs to be 100 newtons, pushing in the opposite direction, pushing upward. Right? And the reason being, at least in this case, is that that brick is at rest. Right? That brick's not moving. So Newton's first law says if it's not moving, the net force on that brick needs to be 0. However, that brick, if we just think about it by itself, right? There's a force pulling it down. We haven't gotten into it much, but that's the force of gravity, right? So gravity is pulling it down. In order for it not to start moving, there needs to be another force on it pushing it up, right? That's the support force. You put it on the gold brick on that table, gravity's still pulling it down. It still has that 100 newtons pulling it down, but the support force is balancing it out. So in total, the net force on this brick is 0, meaning it can be just at rest. Right? Newton's first law, net force on an object is 0, it's either at rest or in uniform motion. This case is at rest. Yeah. That's a question I kind of already answered here, so that's cool. Yeah, so like I said, that support force is a force that always sort of opposes an object kind of crushing or pushing through a surface, right? So another example is like a book on a table. That book has a certain amount of weight, which means gravity is pulling it down with a certain amount of force. And that force, so that the book doesn't just push through the table, that force is balanced or is opposed by this support force from the table pushing it up. Right? So you have the force of gravity pulling it down, you have the support force pushing it up. In total, there's no net force because the support force just balances out that force of gravity. Yeah, so the support force doesn't need to just be on a flat surface, right? If I lean against this wall, there's also a support force from this wall onto my fist to stop my fist from pushing through the wall. Right? So anytime you have an object and it's sort of resting or resting on a surface but not pushing the surface or not moving that surface at all, there's generally a support force that's stopping that movement. So even if I push into this wall, I'm exerting a force on the wall, but the wall's not going anywhere because it's exerting its normal force back out on my normal force, support force. So this is the same. So I guess one way to think about the support force is essentially like when you push down on a surface, or when I push into this wall, it's almost like I sort of start to compress the atoms that make up that wall a little bit, and the atoms then act sort of like a spring, where when you compress them, it gets sort of more and more difficult to compress it more, and eventually you just can't compress it anymore. So by pushing against the wall, it's sort of like I'm squeezing a spring together, and eventually, pretty quickly, that spring just stops me from continuing to move. So that's where you get this sort of idea, where the normal force, you can kind of think of it as being like trying to push a spring down or something. And I guess it's even more useful in the analogy because a spring is something that generally, if you imagine pushing against a spring or trying to compress a spring, that spring pushes back, right? So this is the idea behind, or part of the idea behind the normal force. It's a force where you try to push against something, it always pushes back. That's the support force. Right, so that's the end of lecture 2, I believe, on Newton's first law of motion. Next time we're going to take a short break from Newton's laws and talk a bit about linear motion, or motion in a line. Alright, so be well, and I'll see you later.